Hello friends, today going to start our another lecture is resonance energy from thermodynamical data. So in last lecture we saw the numerical problem which is based on different concept. Okay, so today we're going to start the another topic is resonance energy from thermochemical data. So in chemical energetic, the resonance energy, it is another kind of energy which is exist in some molecules. So here we're going to understand how resonance energy is obtained from the thermochemical data which is already provided or which is given to you. So what is the resonance energy? So it is the energy difference between the two electronic states. One electronic state, it is a located state, means localized bonding, and second is when there is a delocalization of the bonds, means electrons. So that time there is a change in energy. So we get the energy difference between the localized bonds and delocalized bonds. So localized state, electronic state, and delocalized electronic state, the energy difference is the resonance energy. Both are the thermodynamic energies, both are the enthalpies at a localized bonding state and delocalized bonding state. But the difference between them is the resonance energy, because the change in energies between these two stages because due to resonance exist in a given molecule. You are already familiar with resonance. What is the resonance and how it implies in a different kind of molecules? Because in you already studied in organic chemistry, there is a resonance effect. Okay, so for to understand this resonance energy, because resonance energy make a molecule more stable. So due to these consequences, if molecule get a extra stability and due to the presence of this energy, we call it resonance stabilization energy. Basically, any molecule which has a lower energy, their internal energy is lower, getting a more stability as compared to another molecule or another state having the higher energy. So lower energy state always in a stable condition, so the energy goes decreases due to resonance. That means molecule achieve the more stable state due to lower in energy. That means it happened due to resonance. That's why the called as resonance energy. For simple, how we understand it, you know the benzene. So is the benzene, in benzene is a cyclic conjugated planar structure C6H6. Okay, so when benzene is there, benzene itself undergoes the substitution reactions and it retard the addition reactions. It does not undergo addition reaction due to conjugation of bonds or due to resonance in a double bonds. So there is a conjugation. Conjugation means there is alternative double bond, double, single, double, single, double. Okay, so is the structure of benzene. Benzene has 3 double bonds, and you know, if any double bond is it is an isolated double bond, when undergoes addition of H2, it converts into single bond. It converts into single bond. So addition of H2 called as hydrogenation. Called as hydrogenation. So when hydrogenation takes place on any isolated double bond, that time there is a heat is evolved. Heat is evolved and it is the minus 29 kilocalorie per mole. And this energy called as heat of hydrogenation. It is the heat of hydrogenation. Okay, so every isolated carbon-carbon double bond has minus 29 kilocalorie per mole is the heat of hydrogenation. If we considering this value, what we expect here, benzene has 3 double bonds. So what we here expect, the benzene should be present 3 into minus 29 kilocalorie per mole is energy is equal to, it is a minus 87 kilocalorie calorie per mole. It is the expectation according to given data, because the double bond has the heat of hydrogenation minus 29 kilocalorie. It is the expectation, it is the correct, but actually experimentally the measured value of benzene is, experimental value is, benzene has near about minus 50 kilocalorie per mole is the experimental value of benzene. That means here is a difference between the two energy state. If we consider all the bonds are localized, there is no delocalization of bond, they remains here. As that time every bond should be undergoes a hydrogenation reaction. If all the bonds undergoes hydrogenation reaction, suppose goes, that time we expect the minus 87 kilocalorie per mole is the energy. But here the energy is minus 50 kilocalorie and benzene does not undergoes the addition reactions. That means there is a no addition here. So the bonds are delocalized. The bonds are delocalized this way. And we get the another structure of benzene is like that. What happened here? Just the position of double bonds are changed. So this is the resonance. This is the resonance. Both are same. So here the difference is here minus 37 kilocalorie. The difference is minus 37 kilocalorie is the resonance energy. Is the resonance energy. The resonance energy is there. That's why the total enthalpy, total energy of the benzene decreases up to minus 50 degrees Celsius as expected minus 87 kilocalorie. So not a degree Celsius, it is a kilocalorie. So as compared to minus 87, benzene has only minus 50 kilocalorie. This differences is the resonance energy, resonance stabilization energy. So using this data, it is a thermochemical data, because thermodynamics says if there is a localized bond, the benzene shows or expected the minus 87 kilocalorie is the energy, but in a delocalized state, benzene has minus 50 kilocalorie. So the difference between it is the resonance energy. So if we know the thermodynamical data or thermodynamic or thermochemical data, we can predict the resonance energy, how much resonance energy is present in given reaction. So it is all about the resonance energy. We move to the next point regarding this. It is the variation of heat of reactions, variations of heat of reactions with the temperature. So we are going to discuss it, variations of heat of reaction with the temperatures. So point is variation of heat of reaction with temperature. Means how heat of reaction is related or vary in their value with the temperature. So this is the explained by Kirchhoff's equation. Kirchhoff's equation. Okay, so according to this, I already provided you a notes. So when heat is evolved or heat is absorbed, when heat is evolved or heat is absorbed, it depends on temperature, in which temperature reaction is carried out. So how much heat is evolved or how much heat of absorbed will depends on at which temperature reaction is carried out. So this thing is introduced by the Kirchhoffs, and he stated their statement, the change in the temperature, the change in the temperature or the change in heat of reaction at a constant pressure for every degree of the temperature is equal to heat change in the heat capacity at a constant pressure. I again repeat here, the change in the heat of reaction at constant pressure for every degree of temperature is equal to change to the heat capacities at constant pressure accompanying the at the reaction. Means the change in heat of reaction at every degree of temperature is equal to change in heat capacities of the reaction at constant pressure, or in some cases at constant volume. So this is the statement by the Kirchhoffs to explain the variations of heat capacity, heat of reaction with the temperature. We are going to discuss in detail. So let us consider simple. Here we consider simple reaction is A when A converts into B. So A is the reactant, B is the product. Okay. So A converts into B. That time the heat of reaction is a reaction is carried out at a constant pressure condition. So in that case, to understand this phenomenon, this equation, we consider here two cases. If reaction carried out at constant pressure condition, and secondly the reaction carried out at a constant volume condition. So at constant pressure and constant volume condition, how reaction is proceed, and what is the how heat of reaction is changed with the change in temperature. Okay, we are going to discuss one by one. For that we draw some diagram. It is a diagram given here, and the diagram is, suppose we consider this diagram. Okay, so here is a point A, in book there is a mistake, here is a point B. At point B the temperature is T2, at point 1 temperature is T1, at point A at reactant side there is a temperature is T1, and at product side the temperature is T2. So here the change in temperature delta H2, here is the delta H1. Okay, this side is the heat capacity of reactant minus T2 minus T1, and this side is the heat capacity at constant pressure of B minus T2 minus T1. I write here is the Cp of reactant A minus T2 minus T1. Okay, so basically the formation of A into B from A by using two routes. First of all we choose here this route, first route, and secondly this route. Okay, so for route, this is the path 1, here is the path 2 or route 2. For path 1, it is a stage 1, stage first, here is a stage second. Okay, for route second, here is a stage 1, here is a stage second. So we use this diagram, we refer this diagram. So basically heat evolved at the temperature T1 consider as a delta H1, and when heat evolved at temperature T2 as a consider as a delta H2. So heat evolved and heat absorbed, there are two things. So at this stage first there is a heat is evolved at temperature T1 we consider as a delta H1, and heat evolved at temperature T2 is considered as a delta H2. So the stage 1 there is a heat evolved, and here again heat evolved at temperature T2. So the first route, if this stage is heat evolved, here what happened? T1 to T2, the rise in temperature, the temperature is up, that means increase in temperature. So some heat is enter, heat is added. So this step called as heat absorb. Heat absorbed. Again here, the stage first of the route second, there is a T1 into T2, and then reaction proceed at constant temperature. Actually is the process. Reaction proceed at constant temperature T1, then increase the temperature. So in route first, the temperature rises or increases in stage second, but in route second, the temperature rises or temperature increases first, then reaction proceed. Here reaction proceed, then temperature increases. So here, if temperature increases, that means heat is enter, so we called heat absorb. Heat absorb. Once you understand what happened during this reaction, you will understand uh, how this reaction takes place and how we derive the Kirchhoff's equation. First of all, I check it here. You clearly see the diagram. Yes, diagram is clearly visible and see to you. So here, I repeat again. What is the given here? The A to B is the reaction we consider. Okay, and what we're going to understand how heat of reaction is variable with temperature. And according to Kirchhoff's statement, the heat of reaction change at every degree of temperature is equal to heat capacities at constant pressure in a reaction which is accomplished. Okay, so it is the statement. म्हणजेच जर हीट ऑफ रिएक्शन ही पर डिग्री सेल्सियस चेंज होत असेल तर ती किती चेंज होते ऑलवेज इक्वल टू हीट कॅपॅसिटी चेंजेस at a given constant pressure or at given constant volumes, if we see later in later case. So this is the diagram. So here we consider this diagram. So we consider two steps, two stages, two temperature T1 and T2, T1 and T2. Okay, so when A converts into B or A converts into B, so here this is the diagram. We refer to routes. This root, this is a root 1, here is a root 2nd. Okay, so when we consider root 1, so there are two steps, two stages, stage 1, stage 2nd. For root 2nd, this is a stage 1, stage 2nd. This is a constant temperature because this is a parallel line. Okay, same. So at T2, the heat of reaction is considered as a delta H2, and at temperature T1 the heat of reaction or heat is evolved considered as a delta H1. Okay, these are the two heat of reactions, heat of evolved. So when there is a constant temperature, this is a heat evolved, the temperature is increases, that means heat is absorbed. Here temperature increases, heat is absorbed, the temperature constant, heat is evolved. So heat evolved and heat absorbed, there are two important stages in both the route. But what is the difference? In route first, the heat evolved first, then heat absorbed. For route second, heat absorbed first, then heat evolved. So we consider both the routes here. So here we consider route first. We consider route first. Okay, so if we consider route first, the reaction performed at temperature T1 and it reaches to the temperature T2. Okay, so when it reaches temperature T2, at first stage heat evolved is equal to how much? There is a delta H1. Heat evolved, how much? There is a delta H1. At stage second, heat absorbed. How much heat is absorbed is equal to, this is the heat absorbed. Heat capacity of B minus T2 minus T1. Heat capacity of product minus T2 minus T1. So this is a two process in a route first. Okay, so using this, this Cp B is equal to what? It is the heat capacity. It is the heat capacity of product B at constant pressure. At constant pressure. Okay. First of all, you understand this thing, you easily understand how much net heat is evolved. So in first state, heat is evolved. In second state, heat is absorbed. So net heat evolved is equal to net heat so net heat evolved is equal to, so heat evolved in first stage minus heat absorbed in second stage. So delta H1 minus heat capacity at constant pressure of B minus T2 minus T1. We get this is the first equation. So in a root first, if we consider root second, so we consider here root second. What happening in root second? In root second, in a first stage, there is a heat is absorbed because heat temperature rises from T1 to T2. So heat is absorbed, and at second stage, the temperature remains constant. That time heat is evolved. So at first stage, heat absorbed. At second stage, heat evolved. Okay, so at first stage heat is absorbed. How much? This is the value is equal to CPA minus T2 minus T1. And how much heat is evolved here? There is a delta H2. So here the heat is evolved is equal to delta H2. What is a CPA? It is a heat capacity of reactant A. Heat capacity of reactant A. Okay. So if we consider, okay. So heat as the first stage, this is the heat absorbed. At second stage, heat evolved. So what is the net heat evolved during this root second? So net heat evolved is equal to heat evolved minus heat absorbed. So delta H2 minus CPA minus T2 minus T1. We get the second equation. So root 1, the net heat evolved is equal to this one. For root second, the net heat evolved during is the second one. According to conservation of energy, the root A and root B has same process, means both has same heat evolved. Both has same heat of reaction according to conservation of energy. If we use this path or this path, both having same energy. So net, according to law of conservation, net heat evolved at root 1 is equal to net heat evolved at root second. Okay, so net heat evolved at root 1 is always equal to net heat evolved at root second. That means if we put the equations here, delta H1 minus Cp of B minus T2 minus T1 is equal to delta H2 minus CPA minus T2 minus T1. Both are having the same. Up to this you will understand it. Root 1, root 2 both having same net heat evolved according to law of conservation of energy. So after that what happened? So using this thing, delta H1 plus delta H2 upon T2 minus T1, we get this is equal to at constant pressure, at a heat capacity at a constant pressure. So change in heat capacity of at a constant pressure, So using this equation, the delta H1 plus delta H2 upon T2 minus T1, we get the another is equal to change in heat capacity at a constant pressure. So this is very important. Once we know this, we get this equation according to first case, the reaction carried out at a constant pressure. Same thing, the second case is reaction carried out at constant volume. Constant volume. If volume is kept constant. So again you already know, so delta H is equal to delta U plus P delta V is the thermodynamic equation, but here delta V is equal to 0 because there is a constant pressure, change in volume is 0, that means just delta H is equal to delta U. Delta H is equal to delta U. If we put the value of this in given equation, we get same equation, delta U2 minus delta delta U1 minus delta U2 plus delta U2 upon T2 minus T1 is equal to change in heat capacity at constant volume. Change in heat capacity at constant volume. We getting the same equation. There we constant the pressure, here we solve same as given, and here is the volume is constant. So we get the equation delta U1 plus delta U2 or delta U2 plus delta U1 both are same because there is a plus sign. So delta H2 plus delta H1 or delta H1 plus delta H2, or here why we consider delta U, because we have this equation in that change in temperature is change in volume is 0 because there is a constant volume. So we neglect this one. There is no importance on pressure because we carried out the case or reaction at constant volume condition. So we have only delta H is equal to delta U. Both are same. So we replace the delta H by delta U. So delta U1 plus delta U2 upon T2 minus T1 is equal to delta CV. What is the meaning of change in heat capacity at constant volume? What is the CP? Change in heat capacity at constant pressure. So use these two equations. These are the Kirchhoff's equation used to solve the numerical problems in given reaction condition to find out the heat of reactions. So it is all about the variation of heat of reaction with the temperature according to Kirchhoff's equation in the two cases at constant pressure and at constant volume. So we are going to solve the problems. So what is the statement for second case? In first case and in second case. In second case, the change in the heat of reaction at constant volume for the every degree of temperature is equal to change in heat capacities at the constant volume. And in first statement says the change in heat of reaction at constant pressure for every degree of temperature is equal to change in heat capacities at the constant pressure. So there is a constant pressure, here is a constant volume. So you write both the statements for first case and for second case. So we are going to solve the problem which is based on Kirchhoff's equation, and then we stop here. So we are going to write first example based on it.